Okay, so let us start multiple integration today. What do you know about the single integration, or if you given the function y equal to f of x bounded from a to b, then how do we find the area? So let us discuss it first. So we have given y is equal to f of x, where a less than or equal to x less than or equal to b. Then the geometric interpretation of this is say this is the function y equal to f of x from x is equal to a to x is equal to b, and the function y equal to f of x. What we want, we are interested in to find the area of this particular region R. So by the definition of the integration, what we do actually, we divide the domain x is from a to b into this domain x is equal to a to x is equal to b into say n equal parts. So these are equal parts, and then we are drawing the rectangles. So this is how we are dividing the region into the approximated set of the rectangles. Then for the particular ith rectangle, say this length is delta xi, and then corresponding height is f of xi. Then what we do, the area of this particular rectangle is f of xi into delta xi. Then we collect all these area of the rectangles, and then we take sum over it. So summation from I is equal to 1 to n f of xi into delta xi. This is an approximated area of this region. Now when we take limit n tends to infinity, what does it mean? We make this length smaller and smaller, more smaller this length. Then this becomes integration over a to b f of x dx, and this is nothing but the area of the region R. So this is how do we find the area. Now in place of the function f of x, suppose we have given the mesh z is equal to f of xy. Given z is equal to f of xy, where the range of x is say a to b and the range of y is say c to d. Then now we want to find the volume of this object. How do we find the volume? So for example, for some particular f of xy from x is a to b and y is c to d, what is happening? Suppose this is the surface we have given. This is z, and say this is x and y. Then here we have x is from A to B and y is say from C to D, then corresponding to this we have this particular object, and we are interested in the volume of this. So what we do here, concentrate on this rectangle which lies on the xy plane. So say the rectangle is this. We are dividing this rectangle into the meshes and say this is the particular ijth rectangle. So here the length is say delta xi and its width is say delta yj. So what is the area of this rectangle is delta xi into delta yj, and the corresponding for this is delta xi delta yj area rectangle. The corresponding height is f of xi yj. So this is the volume of this particular cuboid. Then we collect all these cuboid and take the sum over its volume. So here summation over I, say it is from 1 to m, summation from j, say it is from 1 to n. Now when do we make this length and width very small, that means we are taking limit n over infinity and m is also infinity, then this becomes f of xy dx dy, and then these are the summations, integrals, where x is from a to b and y is from c to d. So this is how the double integration is defined. This is called double integration of f of xy, where x has bound a to b and y has bound c to d. Let us discuss how does it look like graphically with the particular example. So as you observe, this is the rectangle on xy plane where we have divided x into 6 equal parts and y into 5 equal parts, and then this is the function, particular function, this is 5 minus x square upon 2 minus y square upon 4, and how the cuboid, the set of cuboid is approximated to the volume. Now our task is to increase the number of rectangles on xy plane. So when we increase the values of m and n, it is converges to the exact volume. So this is how do we define the double integration of f of xy. Now before starting the examples, let us understand the terminology. What we have given, f of xy, where a is from a to b and y is from c to d. And what is our target? Our target is to evaluate double integration of f of xy dx dy. Now you know what is dx dy. Dx dy is the area of very small, infinitesimal small rectangle. So for the area you may write down either it is dx dy or you may note down it is dy dx. Now for very small, very infinitesimal small rectangle, the area is dA, then we may note down it by dA also, right? So this particular quantity can be represented by this or by this. Only we need to take care about the limits of the integrals. How do we write the limit? So this is called inner integral with respect to x. So we write the limit of x is from a to b, outer limit of y. So the range of y is equal to c to y is equal to d. Here the inner integral is with respect to y. So we write y is equal to c to y is equal to d, and the outer integral is with respect to x. So we write x is the limit of x is equal to a to x is equal to b. So x is inner and y is outer here. Here y is the inner limit and x is the outer limit. Okay, so I hope this is clear that how do we expand the definition of the area of the region R to the volume of the surface S. So area of the region R defined by single integration, volume of the region is defined by double integration. Now let us start some very simple example to find the volume of very simple surfaces. Evaluate integration over 1 to 2, integration over 0 to 4, 2xy dy dx. So before starting the exercises, you need to understand which are the limits of y, which are the limits of x. So integration over 1 to 2, integration over 0 to 4, 2xy dy dx, which is equal to, what we do? First we mention what is the limit of x, we mention which are the limits of y. So here in this particular integral, y is inside, x is outside. So the inner limit of y, these are the limits of y. So let us write y is equal to 0 to 4 2xy dy. Then the outer limit of x, so I write for x is equal to 1 to x is equal to 2 dx. Students, you don't make any mistake. First we always mention which are the limits of y and which are the limits of x. So this is equal to, now first we integrate with respect to y because the inner limit of y. So first we integrate with respect to inner integral, then we integrate with respect to outer integral. So here it is 2xy dy. I have to integrate with respect to y. When do we integrate here with respect to y? It is assumed that x is constant. So 2x is the constant quantity. Integration of y is y square divided by 2. And then the limit y is equal to 0 to y is equal to this is equal to integration x is equal to 1 to x is equal to 2, 2x. Here you can cancel out 2 and 2. So let me write only x multiply by y square. But here what is the limit of y? Y is equal to 4 to y is equal to 0. So this is 4 square minus 0 square dx, which is equal to integration x is equal to 1 to x is equal to 2. 4 square is 16 minus 0. So this is 16 into x dx. Now this is our usual integration. 16 is constant. We will take it outside. X has integration x square divided by 2 from x is equal to 1 to x is equal to 2. And so this is equal to 16 divided by 2 is 8. X square, that is 2 square is 4 minus 1 square is 1, and therefore the answer is 24. What is the left hand side? Integration over 1 to 2, integration over 0 to 4, 2xy dy dx. I repeat the example again. 2xy dy dx. First we integrate with respect to y. So you observe, when we integrated with respect to y, after that everything is in terms of x only. Just observe here, everything is in terms of x. Then we integrate with respect to x, we substitute the limit, and the final answer is always the number.